Hello and welcome to the fifth and final part of Unit 9. In this part, we're going to focus on elastic collisions. To begin with, we're going to go back to the simulation we looked at previously in inelastic collisions and pay attention to the kinetic energy. Okay. When I have it set at perfectly elastic, I start at 0.44 joules. Oop. And we can see that after the collision, it is again at 0.44 joules. I can make changes. So for example, I can increase the initial velocity of object 2, making the kinetic energy now 1.16 joules. If I again click play, oh, apparently it can collide with the edge too. Who knew? Regardless of what it did, it's still at 1.16 joules, as long as I keep everything elastic. So as a reminder, elastic collisions conserve both energy and momentum. Okay. This very much restricts what the final velocities of these objects can be for an elastic collision. There's only one set of final velocities that will solve both the energy and momentum conservation equations. To begin with, we're going to start with a derivation. Now, I did not see this derivation in your book, which was kind of interesting to me, but it makes doing the math for calculating elastic collisions much easier. Okay. To start this derivation, I'm just gonna show you something because we will need it later. So if I take the dot product of a plus b with a minus b, that ends up with a dot a, or a squared, plus b dot a, and then I end up with a minus a dot b, and then plus a, not a plus, sorry, that should be a minus. Let's fix that. Minus b dot b. Now remember, the dot product is commutative, meaning that b dot a equals a dot b. So these two cross terms cancel, and we are left with a squared minus b squared. Now, we're not given any information about what these two objects are doing. We just know that they collide. So our momentums are going to be very, very vague. So I'm going to do MA VA initial, leaving it as a vector, plus MB VB initial, again leaving that as a vector. The final momentum will be very similar, but instead of initial velocities, I'm going to have final velocities. And now momentum has to be conserved. So initial momentum has to equal final momentum, which tells me that MA VA initial plus MB VB initial has to equal MA VA final plus MB VB final. For the next line, I'm going to take and move all of the terms with involving mass A to one side, all the terms with mass B on the other side. So that's MA VA initial minus MA VA final, and that equals MB VB final minus MB VB initial. And now I'm just going to factor. So I end up with MA times VA initial minus VA final. And on the mass B side, I'm going to pull a minus sign out as well. That way, I again end up with the initial minus final velocities. Okay, so mark this equation because we're going to need it in a moment. Okay, we're going to use this in just a moment. The next step in this derivation is to look at energy. So the initial energy will be 1/2 ma VA initial squared plus 1/2 mb VB initial squared. The final energy, again, will be very similar, but with all the initials changed to final. Okay. And now it's elastic, so initial energy has to equal final energy. Plugging in those two energies results in this equation. I have a factor of 1/2 in every term, so I can cancel it. Okay. And now my next step is to do exactly what I did for momentum with energy and move everything involving mass A to one side, everything involving mass B to the other side. So that is ma VA initial squared minus ma VA final squared equals mb VB final squared minus mb VB initial squared. And again, I'm going to factor. Pulling a minus sign out as well for mass B, so it's again initial squared minus final squared. The next step is to pull in the math I did at the beginning where a plus b dotted with a minus b gave me a squared minus b squared. Well, here I have one thing squared minus another thing squared. So I'm going to separate this out. Okay, the next step in this derivation is to divide both sides of the equation. Okay, so remember, you can do anything to an equation as long as you do the same thing on both sides. Okay. That same thing on both sides doesn't have to look the same. Okay. So what am I going to divide by? I'm going to divide by the momentum equation that I derived on the previous slide. So that would be ma VA initial minus VA final on one side, and on the other side I'm going to divide by the B side. And again, I'm doing the same thing to both sides of the equation because we've already shown that those two things are equal in the previous slide. And now I can cancel. Mass cancels, and the initial minus final vector piece cancels in both cases. That leaves me with VA initial plus VA final has to equal VB initial plus VB final. Oftentimes, this is rearranged so that you get all the initial pieces on one side. So VA initial minus VB initial equals VB final minus VA final. Looks like I lost an arrow. So now, if momentum is conserved for a two-object system, then this equation must hold, which is a lot easier to work with than the one with the squares up above. And the momentum equation from the previous slide, this one, any version of it really must hold. Typically, I use this one instead of the one that's boxed. So now let's apply this. And we're going to apply this thinking about bumper cars colliding elastically. So just as we did with inelastic collision, it really helps to draw a picture. We are told we have two bumper cars with unequal masses. One is initially moving in the positive direction, the other one in the negative direction. I've chose again to let positive be to the right. So after, I don't have any information. I don't know what these two cars are doing afterwards, and this should be V final A. Sorry. There we go. Okay. I can find the initial momentum. That will equal 300 kilograms times 3 meters per second plus 400 kilograms times negative 2 meters per second, which in total works out to be 100 kilogram meters per second. Afterwards, again, I don't have any information for the velocities, so all I can do is write a generic form in terms of the final velocity vectors. I can use conservation of momentum to equate these two pieces. So initial momentum was 100 kilogram meters per second. Final momentum was 300 kilograms times V final A plus 400 kilograms times V final B. I have two unknowns in this equation. So before I can move on, before I can solve this, I need a second equation. For that a second equation, I'm going to pull in the one I just derived. So VA initial minus VB initial equals VB final minus VA final. Initial velocity of car A was 3 meters per second. Initial velocity of car B was a negative 2 meters per second because it was to the left. I can now solve this equation for VB final. That will be 5 meters per second plus VA final. And I can plug this into my momentum equation. So I have 100 kilogram meters per second equals 300 kilograms times V final A plus 400 kilograms times 5 meters per second plus VA final. Okay, notice I'm kind of switching my subscripts around a little bit. V final A and VA final are the same thing. I'm just writing them in opposite order. I now have to remove the parentheses. 400 times 5 is 2,000. I'm now going to collect like terms. So that means the 2,000 goes over to this side, becoming negative 1,900. And then I have 700 kilograms V final A, which in other words means that V final A is going to be a negative 2.71 meters per second. I can now take V final A and plug it back in and find that VB final, not VBB, let's try this again. VB final will be 5 minus 2.71, or in other words is 2.29. So we know our final velocities. Let's just take a moment and verify that energy was indeed conserved. The initial energy is going to be 1/2 times 300 kilograms times 3 meters per second squared, plus 1/2 times 400 kilograms times a negative 2 meters per second squared, which works out to be 2,150 joules. The final energy will equal 1/2 times 300 kilograms times negative 2.71 meters per second squared, plus 1/2 times 400 kilograms times 2.29 meters per second squared, which works out to be 2,150.4 joules. And you may be looking at that 0.4 and going, Dr. Murphy, you said those should be equal, they're conserved. Yes, I will agree completely, should be equal because it's conserved. However, we have round off going on in this problem. The final velocities are not exactly 2.71 and 2.29. They're slightly different than that. And because they're slightly different, our energies are slightly different. So the difference there is round off, and indeed energy is conserved. Next, we're going to think about billiard balls colliding. We're going to have a cue ball colliding into the 8 ball, and the 8 ball is initially stationary. So here is my cue ball, there is my 8 ball. This is moving at 6 meters per second. This is not moving. I'm again going to let positive be to the right for this problem. And much like the previous problem, I don't know what they're doing afterwards. So I'm going to leave it generic. Initial momentum will be the mass of the cue ball, which is 170 grams or 0.17 kilograms times 6 meters per second, plus the mass of the 8 ball, which is 0.16 kilograms times 0 meters per second, which works out to be 1.02 kilogram meters per second. Final momentum is going to be 0.17 kilograms times the final velocity of the cue ball, plus 0.16 kilograms times the final velocity of the 8 ball. I can now use conservation of momentum to equate these two. So 1.02 kilogram meters per second equals 0.17 V final Q plus 0.16 V final of the 8 ball. And again, I'm to the point where I need my second equation. That second equation will be that the initial velocity of the Q minus the initial velocity of the 8 ball will equal the final velocity of the 8 ball minus the final velocity of the cue ball. Initial velocity of the cue ball was 6. Initial velocity of the 8 ball was 0, so I didn't even write it down. I can now write that the final velocity of the 8 ball is going to be 6 meters per second plus the final velocity of the cue ball. And I can plug that in. So 1.02 kilogram meters per second equals 0.17 final velocity of the cue plus 0.16 kilograms. I lost units up here. Let's put them back in really quick. There we go. And now I'm going to get rid of the parentheses. 0.16 times 6 works out to be negative 1.02. Where'd the negative come from? Oh, hold on. In my notes, I solved it differently, so I'm going to have to just do this math on my calculator. It's okay. This works out to be a positive 0.96 kilogram meters per second plus 0.16 kilograms times the final velocity of the cue ball. Again, collecting like terms, 1.02 minus 0.96 is 0.06 kilogram meters per second equals 0.33 times the final velocity of the cue ball. And if I divide that out, I get the final velocity of the cue ball is 0.182. So it went from moving at 6 meters per second to barely moving at all. The final velocity of the 8 ball is now going to be 6 plus that number, so that will be 6.182 meters per second. So in many ways, the two balls have exchanged velocities. If their masses had been equal, it would be a perfect exchange of velocity, but they're just slightly different, which is true in real life. If you took and massed a cue ball and massed an 8 ball, they would have slightly different masses. This concludes this part and this unit.